Good morning, respected session chair, distinguished guests, and the fellow researchers. My name is Bishal Kumar from the Power System and Smart Grid Laboratory in Indian Institute of Technology, Gandhinagar, India. So it is my pleasure to present our research work titled Grid Interruptive Power Allotment of an Existing EV Charging Station with PV and the BESS support in TENSYMP 2026. Let's begin with the motivations of this research. The presentation is organized into the multiple sections. First, I will set the tone with the background and the motivation. Then I will introduce the system descriptions of the EV charging station. Next, I will explain the mathematical modeling for the operational cost of the solar PV systems with and the battery energy storage system. Then I will present the EV power allotment allocations model and the incentive mechanism used to improve the charging efficiency. After that, I will discuss the economic analysis and including the annual revenue and the payback period. Finally, I will conclude with the case-wise result and the key finding that demonstrate the effectiveness of the proposed approach. So if you see in the background, the rapid growth of the EVs is placing an increasing stress on the distribution network, particularly during the peak demand period. So while integrating rooftop solar PV and the battery energy storage systems can significantly improve the situations, but the challenge lies in allocating the charging power intelligently to the EVs while maintaining the grid reliability and the maximizing the renewable energy utilizations. So the motivation behind this work is to make the existing EV charging stations more economically sustainable and the grid friendly. By integrating the solar PV and the battery energy storage, we aim to reduce the EV charging tariff, increase the charging station revenue, minimize grid dependency, lower the operating cost, and reduce the carbon emissions. So additionally, the proposed framework offers the scalable solutions that support the sustainable transportations while contributing to corporate social responsibility and the greater public awareness of the clean energy. So the primary objective for this study is to develop a data driven power allotment strategy for an existing EV charging station based on the EV load demands and the battery state of a charge. To achieve this, we integrate solar systems, battery storage system into a unified power flow optimization framework. Switching this EV power allocations model is proposed to ensure the fair and efficient distributions of the power among connected EVs. Finally, the proposed framework is validated through a commercial EV charging station case study to demonstrate the improvement in energy utilizations, operating cost, and the overall system performance in a live data, means a live network. So here we understand the real field operation practice of the existing EVCS in figure 1, having the DC fast charging station from the Sundar Trader Private Limited situated in Kathmandu, Nepal, where the comprehensive analysis of the existing EVCS was carried out from the daily load profile as well as the aggregated day wise energy consumption for a period of 4 months of the EV charging stations was closely monitored to determine the optimal load profile for the EVs, which is presented in a figure 2. So the data was recorded over a 96 time slot per day. You can see in the top of this figure. So each representing the 15 minutes interval, providing a detailed picture of the power consumptions across a day. Whereas in figure 3 depicts the real charging snapshot of one of the EVs during the in-time charging at 27% and out time charged at 98%. Uh, from here we understand the behavior of charging pattern of the each of the. So this figure illustrates the proposed grid interactive EV charging stations architecture. So simply the system consists of a three 180 kilowatt of a DC fast chargers, 350 kilowatt of a solar PV plants, and a 600 kilowatt of a battery energy storage system, and the utility grid connected through the 11 kV, 11 by 415 kilowatt of a transformer into this proposed network into the existing network simply. So the all energy resources are integrated through the common DC bus, which enable the flexible power sharing among the PV system, base, EV chargers, and the grid. During the daytime, the solar PV primarily supply the EV charging demand. Uh, any surplus PV power can either charge the battery or be exported to the grid. Where the solar generations is insufficient, the base discharge to the support and the charging load, and the grid provide the remaining power only when required. So this coordinated operations improve the renewable energy utilizations, reduces the grid dependency, and enhance the overall economic performance of the EV charging station. Whereas in a table, in a right side of a table present the operational cost analysis of a proposed EVCS with the solar PV integrations, calculating the PV system's cost benefit analysis. So the equations listed here are important to understand the flow of a general mathematical modeling used to determine the levelized tariff for the solar PV plant. Particularly, these equations are related to the sub equations. So considering all these factors, the LCOE, that is the levelized cost of energy for the battery, provides a comprehensive picture of the average cost per unit of energy the base deliver over its lifetime, as shown in equations 20 to 23. This helps to assess the economic viability of the base project compared to the traditional generation resources. So the objective is to decide the optimal charging of the base when the PV power generation is at peak level. Meanwhile, during the non-sunshine period, the base is optimally discharged, followed by the equations 24 to 29. And the rest are the nomenclature supporting to this mathematical modeling of the equations. So equation 30 depicts the total demand of EVs at a time t, where equation 31 and 33 represent the switching sequence for the brand B1, B2, and B3 to obtain the specific charging profile for the particular EV. These equations ensure that once the specific EVs is connected to the charging station, it will follow the charging power profile. So whereas equation 32 and 34 has been modeled to verify the once the S means the switching of the K number of return into the time t, then it cannot be turned on for the period of a t plus 1, t plus 2, t plus 3, t plus 4. Similarly, for the L and M number of EVs. Whereas equation 35 depict the maximum number of EVs that can be catered at a given time t, meaning that the four guns are present, so the four EVs can be connected simultaneously. Equation 36 illustrates the number of consecutive time slot for the each branch of the EVs connected to a DC fast charger depending upon the charging profile. Whereas equation 37 means the total energy consumed over the one complete scheduling cycle and during the sunshine hour. And equation 38 represents the switching the power balance for the different brands of EVs with a range level of SOC for the entire number of EVs arriving at a time block T. So whereas equation 39 and 40 represent the optimal power sold and the bought during the EVCS operations. The power balance of the EVCS infrastructure under the various cases has been depicted in equation 41, 41, 42, and 43, and the equation 44 is a non-linear. So the big M methods has been adopted in this study to linearize the equation 45, whereas the equation 46 ensure that the charging power for each EVs always remain within the permissible minimum and the max limits throughout the scheduling horizon, ensuring safe and the feasible operations. And to propose an incentive scheme, the tariff for the buying and the selling of the power from the grid and the charging station, whereas from the PV, is considered to formulate the profit difference and cost saving percentage in equations 47 to 50. Whereas in equation 51 represent the incentive delivered to find the EV's owner profit. And, uh, and the rest are the nomenclature which support the equations. This slide proposes the mathematical modeling work for the different case studies based on the various scenarios of the grid-tied solar PV systems and the base with and without incentive models within the existing charging stations infrastructure. So here the main objective was to minimize the energy cost by utilizing the cost for the purchasing and the selling of the power from the various resources to find the optimal operational cost. So here you see the figure 5 to 5, 6, 7, and 8 present simply the optimized power allotment profile for the different case studies. So the red bar represents the available PV generations, the blue bar indicates the power exported to the grid, the green curve shows the um, EV charging demand, and the magenta dashed one line represent the grid power input. So it can be observed that the proposed optimization effectively utilize the available solar energy to meet the EV charging demand while minimizing the grid dependency. During the period of excess PV generation, the surplus energy is exported to the grid, whereas during the low solar generations or high charging demand, grid power is imported only when the necessary. Across all case studies, the optimized strategy ensure efficient power allocations and improve the renewable energy utilizations here and enhance the overall economic performance of the EV charging stations in all different cases. So this table simply compare the economic performance for the different cases of the PV power EV charging stations. with the terms of an annual revenue, payback period, and the long-term profitability. So if you see the base case, achieve our annual revenue of a $24.37 thousand with a payback period of a 4.46 year. Among all the proposed cases, case to provide the best economic performance and increasing the annual revenue to the 47.14 thousand dollars, generating the additional 390.45 thousand dollars, and that is the highest profit margin of a 78%. Although some cases has a slightly longer payback period, they deliver a significantly higher long-term profit compared to the base case. So overall, the result demonstrate that the integrating PV and the intelligent energy management can sustainably improve the profitability and the economic viability of a EV charging stations, with the case 2 emerging as an optimal solution. So the key outcomes of this study are as follows. We can see here the proposed grid interactive power allotment strategy effectively coordinates solar PV, battery energy storage systems, and the utility grid to meet the EV charging demand. It maximizes the utilizations of the renewable energy, reduce the grid dependency, and lower the EV charging cost. So the optimized energy management also improves the annual revenue and profitability of the charging stations while maintaining the reliable charging service. Overall, the proposed framework demonstrate that so that integrated PV and the base with intelligent power allotment can significantly enhance the technical, economics, and the environmental performance of the existing EV charging stations. Thank you all for your kind attentions and the valuable time. I sincerely thanks the organizer of a TENSYMP 2026 for providing this opportunity to present our work. I would also like to express my gratitude to my co-authors and my supervisor for their continuous guidance and support. So thank you all so much. I would be happy to answer any questions you may have here.